I need a verb, and they are supported by the point in which they meet. So that's my concept. I'm trying to reason in terms of mixed V's. Yeah? Now there are two theorems, two very simple theorems. The first one is that each node supports at most 6 mixed V's. You see? If all 5 edges that meet in that point have the same color, there is no mixed V at all. Yeah? If the color division is 1 of the one color and 4 of the other, then I can form 4 mixed V's, because the one of the one color can be combined with any of the remaining 4. However, if the division is as equal as possible, 2 of the one color and 3 of the other color, then I can in 6 ways select 2 edges of a different color. So the theorem is that a node supports at most 6 mixed V's, where 6 is formed as 2 times 3. That is when 2 of its meeting edges have one color and the remaining 3 the other. So there we are. The other remark is that if we look at a bichrome triangle, I can select 3 V's by omitting one of the sides. The other 2 sides form a V. If I take a bichrome triangle, then 1 V is monochrome and 2 of them are bichrome. Yeah? The ones meeting at the bottom, that they are of different color, and the ones at the top are of the same color. Now, since each V already contains 4 edges, it is 3 nodes, it determines the triangle in which it lies uniquely, and therefore those 2 mixed V's occur nowhere else. And the moral of the story is that no matter how you color, the number of mixed V's is twice the number of bichrome triangles. Each bichrome triangle absorbs 3 mixed V's. A monochrome triangle doesn't contain mixed V's at all, because it's homogeneous. So the number of mixed V's is twice the number of bichrome triangles. Now that's quite general. And now we go. Our proof obligation, the top line, is the Boolean statement that a number of monochrome triangles is at least 2. That was a theorem we had to prove. Now remember, from my very first foil, the total number of triangles is 20. And since each triangle is bichrome or monochrome, if the statement that the number of monochrome triangles is at least 2 is equivalent to the statement that the number of bichrome triangles is at most 18, 20 minus 2. But our previous corollary says that the number of bichrome triangles is half the number of the bichrome V's. So thanks to the corollary, that statement is equivalent to the remark that the number of mixed V's is at most 36. Now each mixed phi is supported by a node. There are 6 nodes. So that the total number of mixed phis is at most 36 follows from the still unproven fact that each node supports at most 6 of them. But that was lemma 0. Each node supports at most 6 mixed phis, and lemma 0 says that that is true. So here we are. And notice that this second argument is much less laborious than the case analysis we struggled with beforehand. Secondly, it is quite straightforward to generalize this argument to smaller or larger graphs. If you do this, try this on the complete 5 graph, you'll discover that there need not be monochrome triangles at all. And another illustration is that shows from this example, this argument, that you get the minimum number of monochrome triangles, provided that you make as many mixed phis as possible, and that you get if at each node you support as many mixed phis as possible, which happens if 2 are of the one color and 3 are of the other color. Here is my original graph, and this is one with only 2 monochrome triangle, and you look at the 6 points, and you see that the color frequencies at each matches 2 of the one color and 3 of the other, as it should. If the distribution was not so equal, there would have been more monochrome triangles. I think this was a wonderful piece of timing. If you wish to shoot at a pianist, this is the moment to do it. Are there any questions, remarks, objections? Questions about other things? Yes, sir.
I'm not sure whether this is a remark or a suggestion, but it seems plausible that in some other theorem, like the 8 graph or something, the counting argument might only be able to prove the weaker theorem than the case.
Sure. I have not demonstrated that the counting argument gives the sharpest bound. It does, but that's a more complicated argument. It is, I did not write it down because